Bismillahirrahmanirrahim. I am Muhammad Ehsan Jatta, Professor, Government Degree College Chichawatne, Department Chemistry. Dear student of the first year, today lecture is about chapter 11, Chemical Kinetics, and its article about Arrhenius equation. Arrhenius theory, Arrhenius equations. Dear student, Arrhenius equation is the relationship of the rate constant denoted by K and energy of activation represented by capital E and small a. The whole equation, Arrhenius equation, is equal to rate constant K is equal to capital A. Capital A is known as collision factor, pre-exponential factor, and it is also known as affective or non-affective collisions about this A. E is the log base and its raised to power energy of activation minus divided by R universal gas constant. T is absolute temperatures. Energy of activations can be determined by these equations from the Arrhenius equation. Again, listen. K is the rate constant. T in this equation is the temperature in Kelvin scale. Capital E and small a is the energy of activation, and R is the ideal universal gas constant. Its value is 8.3143 joule per Kelvin per mole, and A is the frequency or pre-exponential factor. In this equation, this equation is utilized to determine the energy of activation from the rate constant. The collision frequency and orientations are both are specific for energy of activations. Dear student, energy of activation is the energy required to convert the reactant into their activated state. They form activated complex at this stage, and again they change to the product if the reaction has been carried out. If the reaction is not carried out, collision are ineffective, that activated complex return back to the reactant. The process of the chemical reactions as the reactant transforms to the product can be described graphically. Reactant start to cover the barrier of the energy of activation. So the energy of activation is higher than the energy of the reactant. Then after transition state, the reactant are converted into product, and this is take place in exothermic reaction, and the difference between the reactant and product energy is actually the energy evolved in the exothermic reaction. Reaction progress in shown in the diagram. Similarly, reaction coordinates, energy graph, again reactant take energy to convert into activation energy, that's also known as a rate determining step, and change to the product as shown in the diagram. In case of reversible reaction, when the reactant reverses into the product, a reactant have much less energy. In reverse reaction, they have to attain the maximum activation energy to attain the barrier of activated complex. They form activated complex in the reverse reaction and change to the product. So, in generally spontaneous or exothermic reaction, the, the reactant again change to the product. They are almost impossible. They have high activation energy barrier that is difficult to overcome. Energy of activation in the forward action is equal to total energy in transition state minus total energy of the reactant. When we subtract the energy of reactant from the energy of transition state, we get the energy of activation. A reactant cannot proceed unless the reactant possesses energy equal to activation energy. It is very important condition for any reaction. Again listen, reaction cannot be proceed unless the reactant possesses the energy equal to activation energy. Change in energy, the thermodynamic quantity tells us about the net reaction. Energy of activation must be available in the surrounding for the reaction to proceed at measurable rate. The energy of activation temperature for the system of the particle is described the bit distribution of energy. Some particle fractions have higher in energy and other fraction of the reactant have lower in energy. The fraction which have the energy nearer to the activation energy, they gain energy and converted into product. So, if we supply from the outside, the energy of activation of fraction molecule that have energy of activation increases, hence by increasing the reaction generally the energy of activation complex increases and rate also increases. In endothermic reaction, when we increase the energy, the molecule gain the energy and become equal to activation energy and they are changed to the product. The main and important factor in this Arrhenius equation is the orientation factor. Orientation factor A is also known as collision factor, free exponential factor, This pre-exponential factor actually depends upon the orientation of the molecule during the collision. Either the collision or effective collisions reaction can take place. Generally, the reaction occurs only when the orientation of the molecule are right one. The molecules, different atoms, are they are if properly oriented at their collision point as shown in the diagram. There are ball of the red and green colors. If the red balls and green ball are in same orientation, then effective collision take place and reaction can occur. Similarly, again see in the diagram, if this red and green are not present in the same orientation, green strike with the red, it means that they are not effective collisions, so the reaction cannot be take place. This type of collision is known as ineffective collision. This is known as orientation factor, collision factor, pre-exponential factor in Arrhenius equation. Arrhenius equation discovered the most reaction rate data obeyed an equation based on the three factors. Number one, number of collision per unit times, number of collision per unit time. Number two, the fraction of the molecule that occur with the correct orientation. Number two factor on which reaction depends, number of the molecules that have the correct orientation. Number three on which reaction rate depends is the fraction of colliding molecules that have sufficient energy and their energy become equal to energy of activation. These are three main factors for have indicate by the Arrhenius equation to take place the reaction. Number one, number of collision per unit times. Number two, the fraction of the molecules that collide among themselves, they are proper oriented. If there are proper orientation, effective collision takes place, rate of reaction is increased. Number third, the main important factor is the colliding molecules that have sufficient energy that become equal to the energy of activation. All these observations are developed from the observing the Arrhenius equation. This temperature dependent Arrhenius equations indicate increasing the temperature actually will increase the energy of activation of the fraction of the molecule, and when the energy of the molecule increase, the fraction of the molecule that have energy equal to energy of activation increase. Hence the exponential factor, collision factor, orientation factor, this is the increase, and effective collision are much more in fraction, so the rate of reaction generally increases as observed in Arrhenius equation. Temperature and rate of reaction. Dear students, you know that by increasing temperature, we provide the energy from outside source to the reactant, and the fraction of the reactant increases. They have energy equal to energy of activation. They form activated complex and change to the product. So generally, by the increasing temperature, rate of reaction also increases in Arrhenius equation and generally. Arrhenius noted the rate of reaction should be understood depends upon the energy of activation and absolute temperature in exponential form. If we take log on both sides of the equation and common log, first we take the natural log of the rate constant is equal to natural log of the collision factor minus energy of activation divided by RT. On the basis of this equation, have if we put the values and change the natural log into the common log, we multiply the factors natural log 2.303. The equation become log of the k will be equal to the log of A minus energy of activation divided by 2.303 RT. This equation can be used to calculate the energy of activation. When we plot a graph between the inverse of temperature on taken x-axis and log of natural log of the rate constant k on y-axis, we obtain a straight line that not starts from the region. It is you have start from the y-axis toward the x-axis and straight line, and its slope will be equal to slope of this Arrhenius equation will be equal to energy of activation minus EA over R. So we can determine the slope of the if we are given energy of activation. Energy of activation divided by universal gas constant 8.314, we get the slope of the reaction. This is all about the energy of activation. There, student, today lecture is about Arrhenius equation and its determination of energy of activation. Thank you, student. Allah Hafiz. Take care.